Hello, 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 Gianna, hello, Jose, hello, Ashley, hello, Jasmine, hello, Miriam, hi, Montserrat. Oh, that's a new one. That's a good. Oh, I don't know if you hear that, but yeah, it says hello, Ashley, hello, Jocelyn, hello, Anthony, hello, Brianna. There's more people with. Hello, hello, Jasmine. Okay, hold on a second. Hello. Dog that is mine and making a lot of noise. Yes. Good afternoon, Samaya. Hi, Brian. Hi. Okay. Wait, more people coming. Okay. Okay. Hello, Alejandro. There's more people coming. Top of the afternoon, Abdel. Good afternoon, old smile. Oh God, you can hear that, right? You can hear me, yes? Because I can't hear. Could someone do, can you hear? Oh, can you not hear me? Wait a minute. Could someone confirm or deny? Oh, hello, Sarah. Wait, can you confirm or can you not hear me? Wait a minute, maybe you can't hear me. Could someone confirm or deny? You can. Okay, okay, thank you. Okay, thank you. Okay. Good afternoon, all smile. If I didn't say, oh, and you can. Thank you, Gianna. Thank you, Jasmine. Thank you, Jose. Thank you, Stephen. Okay, okay. And can you, as long as I'm asking, can you hear that? Can you hear Azra? That hi, Sarah. If I did say, oh, hi. Okay. Okay, thank you. Okay, okay. Pardon me for a second. Okay, thank you. You got mail. Also, okay, we're gonna swap here. You also got
You got some switches and some thingies.
oh, you opened them. Oh, capture energy and switch. Oh, you opened them without permission. Pardon me for a second. Well, you thought they were split. Oh, someone's coming. Okay. All right. Pardon me. I'm going to transition you for a minute. I'm going to leave it. Just be careful with them. Are half for me and half for you. I just gave her water, but I didn't give her food.
Okay. Could you open this?
Okay. Okay. And then I'm trying to teach a class. Do you want to split the capture energies and the switches?
I'll take the capture energies.
All of it. You get all of
I'll
them.
take some.
Some. All right. Cool.
Action.
Sorry. I'll be okay. Wait. I actually can't. Probably okay. Sorry. And okay. Pardon me, folks. Okay, wait, Felix. I can't. Hold on. Let me open. Felix, I will open these right after class. I can't. I don't. No, here we go. Okay. And we can play right after class, but there you go. Okay. Okay. Awesome. Good job. And we didn't mess up the decks. We're still in the middle of the match from before. Okay. Sorry. I don't know if you could hear that. So that was my son, Felix. Oh, someone's here in the waiting room. Okay. Okay. Sorry. Okay. Okay. Sorry. I don't know if you guys can hear that, but we're trying to our dog Azra, and we want her. She really wants to be in this class, but she does not have the calculus prerequisite yet. But we're working on that. Okay. Okay. But yes, totally. Hold on. Wait. Yes. Did you private chat person? Absolutely, and for real. Did you recognize the capture energy reference? Is that what, or the switch? But yes, we are avid TCG players. Don't even get me started. Oh, great. Okay, thank you. Other private chat person got you about the. And sorry, this is it. Obviously, sometimes I teach from home, and it's a little bit. Always I teach from home. I mean, okay. And usually it's not as okay. Yes, I see you're on the same device. That's cool. We're gonna get started. Oh, sure. Oh yeah, live transcript. Yeah, absolutely. Sorry. Okay. Oh, wait. Sorry. Okay. But yes, if anybody ever plays Pokemon TCG, I mean the actual card game, come to my office. I mean, I've got decks there. I would be delighted to. But anyway, okay. Switch to start. Okay, let me switch gears here. Here's what's happening. View also. Okay. Okay. So technically still what's due next Monday is homework number 6, which was just posted yesterday. Yesterday, we actually started doing one of the problems of homework 6. And we're going to continue that. So hopefully that helps you. I mean, sometimes you have to do things before we even talk about them. But right now we're talking about them before you have to do them. Maybe that's a nice relief. We're going to continue with that. Today, we're going to talk about another problem that's in the homework that was already handed out yesterday. You're absolutely encouraged and welcome to use anything that we say in class in order, to do that assignment and submit it. So what we're going to be going over, what we're going to be talking about in a moment is problem number 4 from assignment 6. Again, assignment 6, homework 6 is called Big Old Duck. It's called that because the very last problem in the whole thing is a problem called Big Old Duck. It's the most involved or possibly the most challenging or most demonstrative problem of the whole packet. It's really is the purpose of the packet. Most of what is in the packet, the homework assignment is trying to get you to be able to get you to the point of being able to do Big Old Duck. Big Old Duck again ties together concepts from lab 3 and lab 4, some of which we've spoken about, some of which we haven't. Big Old Duck is a problem that usually appears on exams. I'm just telling you that right now. Again, today I don't want to talk about exams or anything like that. We don't have an exam scheduled right now or anything like that, but if you're trying to make notes to yourself of like what to know and what not, the Big Old Duck problem is a signature problem we're trying to get to here. But today we're going to talk in order to get there, we're going to talk about problem number 4 in homework 6. Problem number 4 is called a velocity time graph. We'll turn to that in a moment. But just as another quick public service or sort of like review of where we're at or what's going on so far, starting to have a bit of a list of equations. The list of equations that you see on the board right now, they are not all of the equations that we've done. Like we've done more than just those. What they are, at the same time, there's nothing on this sheet right now. When you're looking at the board right now, all of these equations now are equations we've seen. Like sometimes on the board, I write an equation that we've gotten to, and then I write another equation of what we're trying to get to. Today, every single equation that's on this board, we have gotten to, like nothing that should look, unfamiliar. The 3 equations that you're looking at on the board right now that are labeled number 2, number 3, number 4, all of those, remember, please know, those are all equations that are true when and only when acceleration is a constant, right? When position is changing so that we say there's velocity, and velocity is changing so we say there's acceleration, but the acceleration is not changing, right? Like that's the context we're in right now in physics. And let me say again, it's a very, very fundamental piece of physics, very fundamental. Let me say it again. So I'm going to keep saying it, like for the rest of our lives, in a way, all of physics, in a way, even modern day relativistic physics, even modern day quantum physics, well, a little bit less so that, but almost all branches of physics in a way boil down to the distinction, will boil down to the relationship and distinction between velocity and acceleration. Like, it's really not an exaggeration to say that to really understand how velocity and acceleration are related, but to also understand really how they are different is really at the heart of what it means to do physics at any level. I mean, and I really am serious about that. So there's many ways to look at both concepts, and that's why we keep sort of helixing through them. One way is a mathematical calculus way. I just want to remind you again that velocity is the instantaneous velocity is the instantaneous rate of change of position with respect to time, i.e., velocity is the first derivative of position with respect to time, if you're going to talk about it in calculus language, and acceleration is the first derivative of velocity with respect to time, right? So acceleration is the second derivative of position with respect to time. So the context, so we started the year by doing a lot of examples and investigating velocity and really sort of whether we used math terms or not. Beginning of the year, we were talking about what's going on when motion demonstrates a first derivative, right? And then we pushed it a little bit further and we established this concept of acceleration. So then we are talking about what happens when motion demonstrates or exhibits a second derivative of position with respect to time. Well, if this were a pure math class, if all we were interested in the math is the math theory, we could then go further and then talk about, okay, what happens when acceleration changes? What happens when there's a third derivative with respect to time? We could totally do that. I mean, that would be like logical. And then we could go to the fourth and the fifth, et cetera. There's no reason not to. If we were just thinking in these generalized universal terms of rates of change. You could discuss rates of change to eternity. However, what we're saying in physics is it turns out that in the natural physical external world of space and time, like not just in our heads mathematically, but in the physical world, it turns out that there's a lot of natural and important motions, examples of motion, where there is a first derivative, and there is a second derivative being demonstrated, but there's no third derivative or fourth or fifth. That is, it seems to be very common and very instructive to talk about situations where there's a change in position, but there's no change in the change. I'm not even kidding or trying to be silly. We're looking at situations where there is a second rate of change, but that rate is constant. It's itself not changing. There's a rate of change, but there's no rate of change. That's what I mean. So we have constant change of change. That's what we're talking about when we're talking about constant acceleration. Honestly, like, I'm not trying to make it harder. I'm just trying to put in perspective, like it's like a particular niche that seems to describe a lot of important motions and phenomena in nature. Okay, so constant acceleration, when A equals A naught, both of which together equal A bar, when average acceleration, instantaneous acceleration, and initial acceleration are all the same thing, that's what we're concerned with right now in this class. And now, to be more specific, what I started saying yesterday or Monday, that seems to happen. Like one chief context in which we see that is the context of free fall, when objects are subjected to no influence other than gravity, when objects are just being pulled by the center of Earth, but not being pushed or pulled or touched by anything else, we call that free fall. And we say in that situation, there is a constant, approximately constant rate of acceleration. And so that's where the context we're in right now, right? So we've gone from velocity to acceleration to, well, really, we went from average velocity to instantaneous velocity to average acceleration to instantaneous acceleration. Then we got to constant acceleration. And now we're talking about a specific example of constant acceleration known as free fall. during free fall, you have a rate of acceleration that doesn't change. If you measure that rate in meters per second squared, it's 9.8 or it's approximately 9.8 or approximately 10 meters per second squared. If you measure it in feet per second squared, it's approximately 32 feet per second squared. But you can measure it in any kind of units that you want. The number itself is not magical. The number itself is not given by God or the electron in heaven or whatever. The number just reflects what units we've chosen to measure. And so there's nothing particularly special about the number. What's special about free fall is the fact that the number of acceleration units doesn't change. So we call that number from here on in, the number, whatever the number is in whatever units we're measuring, the number that describes the rate at which we accelerate when we're in free fall, we call it lowercase g, okay? Lowercase g for gravity, but capital G is another aspect of gravity. Just to be clear, we call it lowercase g. Lowercase g stands for the constant acceleration during free fall. Whether we make it positive or negative is up to a coordinate system we've decided upon. And whether we make it one number or a different number depends on what units we've decided upon. All those things are decisions, and they're all equally valid decisions. Thank you, Galileo. But whatever that constant rate is from here on in, when we're in free fall, we're going to refer to it as lowercase g. Last thing I'm going to, and when that's the case, when we're in free fall and our instantaneous rate of acceleration is the same as our initial rate of acceleration, which is thereby the same as our average rate of acceleration, and all of which we're going to call lowercase g, when that's the case, first of all, these three equations on the board all apply. That's point number, right? Like those equations on the board, like the V bar, the one that's labeled number 2, the one that's labeled number 3, and the one that's labeled number 4, they don't always apply, but they do always apply when acceleration is a constant. So they are our constant acceleration equations. Okay, that's number 1. And number 2, the thing. So everything on the board right now is knowledge that we're allowed to use, that we should use and rely on whenever we're assuming we're in a free fall context. Side, like if you're taking an exam or something like that, or in life, and someone just says something, an object is free falling toward the surface of the earth. Right away, that tells you that all these, that means automatically you can use all the information that's on this board right now. That's all of that is implied by the English term free fall. But the reason I'm saying free falling up here, I want to emphasize what we're going to analyze today is a problem where something is free falling, and for some segment of its free fall, it happens to be going up. I want to make clear from the get-go that that is not a contradiction, and that is often true. That the definition of free fall is no influence other than gravity, which means a constant acceleration known as lowercase g. Free fall is a state of acceleration. It doesn't mean anything about your state of velocity other than the fact that it's changing at a constant rate. In other words, velocitizing down is an example of free fall. But velocitizing up can also be an example of free fall. So can velocitizing forward. You can have any velocity at all. You can be heading in any direction, moving at any speed. And as long as nothing is touching you at that moment, as long as nothing is pulling or pushing you other than Earth, then you're in free fall. So if a quarterback throws a football, the minute the football leaves his hand or her hand, the minute a football leaves a quarterback's hand and is off doing its own thing, it was pushed for a moment by the quarterback's hand. But the moment it's not touching the hand anymore, it's now released. It is free falling. It's going to travel up for a while. It's also going to travel forward. That's all statements about its velocity at various moments. But it is being pulled all the while only down toward Earth. So the entire time a football arcs like across the field, or the entire time a cannonball, after being shot out of a cannon, is arcing across a battlefield, all that entire time we call it free fall. And what we mean when we say that is that regardless of what direction its velocity is heading in at any moment, at all times, its acceleration vector is pointing down at a certain constant rate. We mean that all the while the velocities are heading down. At what, say you call down negative and you call up positive, which is not always true, but is often true. If you call numbers that are, if you call down negative and you call up positive, then while a football is going across a field or a cannonball is going across a battlefield, right? Or while something is going straight up, its velocity numbers might be positive, but they're becoming increasingly negative. In other words, decreasingly. If something is shot up with a velocity of 50, positive 50 meters per second, it'll go like positive 50, then positive 40, then positive 30, then positive 20, then positive 10, then 0, right? It'll decrease its velocity by 10 every moment. It'll slow down, then it'll hit 0. And then what happens? Well, the acceleration continues to be a negative 10. So then the velocity will go to negative 10 and then negative 20 and then negative. In other words, when you shoot something up, it goes up while slowing down and then it comes back down while speeding up. The entire time its velocity numbers are getting more negative. If you think about, right? So and the entire time we call that free fall. Free fall means your acceleration is pointing down at a constant rate the whole time, whether you happen to be velocitizing up or velocitizing down. Okay, now, so that's a important point. It's another example of the distinction. The acceleration is the change in velocity. Acceleration is not the same as velocity. So we're going to see that in action today. I mean, I don't know, maybe that was clear, maybe it wasn't, but if that went too fast, what I just said, or if you got that there was something there, but you didn't get the whole thing, good, fine, no worries, because we're about to break that down into a problem that we're going to analyze now. But the reason I call this concept like free falling up is I'm just trying to emphasize right from the get-go, free falling doesn't have to, I mean, it can mean down, but it doesn't have to mean down. The term free fall does not refer to your velocity, it refers to your acceleration. Okay, that said, and please stop me at any time. I mean, I see that there's the transcript running, which I hope, because someone asked, and that seems like a great idea. I have no problem. I hope it doesn't bother anybody that it's going. And I think it ends up in the recording, but I'm not sure. Maybe you could tell me. But I'm happy to do that anytime anybody asks. And it might be because two people are using one device. I'm not sure. That's fine. But anyway, okay. So, so what we're going to do is we're going to go to, we're going to go to homework 6, problem 4. Here we are. So problem 4 is called a velocity time graph. Now, okay, also, everything I say here hopefully will help you be able to do it and hand it in. A lot of what I'm pretty much going to do the whole problem for you, and that's fine. As long as you understand what you're doing, but it's up to you to put this into step 1, step 2 method and stuff like that. So I'm using it as an excuse to talk about other things as well. So problem 4, velocity time graph. What they say in the problem now, also, I'm choosing to show you the screen of my solution. So hopefully you see the problem in front of you. Hopefully you have the sheet, either, on a paper form or on another window in your computer or something. But I have to switch back and forth also. But okay, in the beginning of the problem, they say there's this object that they call Edna for whatever reason. And they tell you to draw this graph of it. So they just give you the graph. And then we're going to infer all this information from the graph rather than the other way around. So they tell you to draw, to label the dependent axis as instantaneous velocity and the independent axis as time. And then they tell you to create a graph that's a straight line graph. They tell you that. I tell you that. They tell you that the slope is going to be -4. So the rise per run will be -4. So for every 1 over, it'll go down 4, right? They tell you that. And I don't know why I say they, I mean, I wrote it, but anyway, whatever. The me of 400 years ago then also tells you, and I don't know why I called it Edna. I don't know what I was thinking, but I also tell you that the y-intercept is 12, +12. So the point, so it intercepts so this straight line that is given there, I'm giving you slope and intercept. So I'm giving you the whole information that you need for that line. So I've made this graph, you can see. And I've labeled 2 key points. The y-intercept is 0, 12. And then just because I know the y-intercept and I know the slopes, that's sufficient information to draw the whole line. I can see that it intersects the x-axis at 3, like because of the slope, right? It goes down 4 for every 1 that it goes over. So it goes down 12, therefore it goes over 3. So I've labeled those 2 points, 0, 12, and 3, 0. Remember, the x coordinate of each one of these points is the x coordinate is a time measured in seconds, and the y coordinate of each point is a instantaneous velocity measured in meters per second. Now, before I do it, and then there's like, obviously this is a somewhat crowded slide here, or crowded board, but I think, yeah, if you look at all that, I want to pause before going any further and say this graph has 3 things, right? It has axes that are labeled, and maybe please make a note of this. I mean, this graph has 3 things. It has axes that are labeled. It has a basic shape or trend, a basic, smooth, and clear, like i.e. in this case, it's a straight line with it's a straight line. And then it has a key point or 2 that is fully labeled with coordinates. Like in this case, there's 2 points that are fully labeled with coordinates. And I'm saying 2 is plenty. I am saying these 3 things, labeled axes, general shape or trend, and a point or 2 that is labeled with coordinates, is what we mean from here on in as a graph in physics. Not so much in the lab. In the lab, often you have to create a full real scatter plot, right, from data that you actually gather. But even there, once you create a scatter plot, the point you'll measure a bunch of stuff in a lab so that you can get information and create a scatter plot. But the point of a scatter plot ultimately is never to connect the dots. I think you've heard this. I hope you've heard this in other science classes. No matter how many points you get from, no matter how much information you gather in the lab, once you have a scatter plot, the purpose of it is never to literally connect all the dots together into some complicated shape. The purpose of the scatter plot is always ultimately to be able to get some kind of smooth, comparatively simple, definitely identifiable shape or trend that captures the pattern of the dots, that maybe goes above as many dots as it goes below, but never to connect the dots, right? The purpose of gathering information in the lab is to get a graph, and the purpose of a graph is to see a trend or a basic shape, a basic pattern, to see whether some relationship is a linear relationship, or if not, if it's maybe a quadratic relationship or a cubic relationship, or maybe a sinusoidal, cosinusoidal relationship. What we want out of a graph is to see the basic form or trend of a relationship. We only know what relationship we're talking about if the axes are labeled, and we only know the scale and a bit of like the details of the relationship if a point or 2 is labeled. So for example, in the case of here, we have this basic relationship that's a straight line. That tells me a lot. That's really what I wanted to know, is what kind of relationship is this? Oh, it's linear relationship. It's direct proportionality. Then I say to myself, what's directly proportional? Oh, I look at the axes. Velocity in this case, or the change in velocity, is directly proportional to the change in time, okay? And then if I want to know the details of that, like I say direct proportionality, that means linear, that means constant slope. If I want to know what the actual slope is, I've got a point or 2 here labeled to show me that, and also really to show me the scale of, like, at what scale am I observing this pattern or trend. But what I'm trying to say, and I'm probably saying this for you, all we ever want from a graph, whether even if it's at the end of a day in a lab, or certainly on an exam or a homework or something, what we want when we say graph, we want labeled axes, we want a basic shape or trend, and a point or 2 that's labeled sufficiently to give us a sense of scale. Okay, that's it. We don't need a million points. Okay, so that's what we have here. We have what we're seeing here, just looking at it, before I even answer any questions, I'm seeing that if I have a velocity time graph, apparently, if I have a velocity time graph for some situation of constant acceleration. No, sorry. Well, yeah, okay, I'll say it. If I have a velocity time graph for a constant acceleration situation, then my velocity time graph will be a straight line. Let me say that in a slightly better way or a different way. And it says it right here on the board. Notice, if we were on a position time graph, if we're not here, but if, like in the beginning of the semester, if we were relating position to time, or we were relating changes in position, i.e. displacement, to time, then what it says here in blue at the bottom of this slide of this sheet is the straight line connecting any 2 points on a position time graph the slope of that line would give us average velocity. The slope of a line connecting any 2 points on a position time graph is average velocity. Hold on. Okay. That's on a position time graph. So I'm saying, so it's very important to see a relationship between slope and average velocity, but don't memorize that. Just don't think, oh, slope is average velocity. No, slope on a position time graph is average velocity. And by the way, why? Because slope is rise per run. It's change in the dependent variable versus change in the independent variable. And if we were in a position time graph, so in a math class, you say like delta y over delta x. So you say like y2 minus y1 over x2 minus x1 equals slope, right? Like in a math class, when you're thinking of this as the y-axis and this as the x-axis. Well, now we're in physics. So if you were in a position time graph, the dependent variable isn't just called y, it's position, as in what we usually call x. And the independent axis isn't just any old x, it's actually the independent variable that we generally regard as time in physics. So in other words, what we generally call t. So on an xt graph, slope would be x2 minus x1 over t2 minus t1, right? It would be change in position per change in time. And what is that called? That's displacement per time. That's velocity, average velocity, right? So if you plot positions versus times, the slope, the rate of change of that is average velocity. And if you take that to the limit, if you shrink it down to just 1 point, then it's a derivative and we call it instantaneous velocity. Okay, so velocity is the rate of change of position with respect to time. But if we took a bunch of velocities, a bunch of instantaneous velocities from some position graph, say we knew about the motion of Edna, say we knew where she was at one moment and the next moment, put that all in a scatter plot, and then took the slopes at various time moments from that scatter plot. If we put those slopes onto a graph, then we would have this graph here. In other words, this graph is not telling us where the object is at any moment. This graph is telling us how fast Edna is going at any moment. This is a graph of velocities with respect to time, right? And then what I'm saying now is, oh, well, then let's take the let's take the relationship one level further. Then if this is a velocity time graph, between any 2 points on this graph, the slope of the line connecting those 2 points will be the rate of change of velocity. Like rise over run on this graph would be like V2 minus V1 over T2 minus V1, or T2 minus T1. Or in other words, V final minus V initial over the interval of time. The slope of this graph would be average acceleration. Okay, again, this is one of those things that to 1/3 of you, you're like, yeah, I know already. Like I've known that for some of you are thinking like, I've known this forever, like please, right? And I apologize. Some of you, well, why do I care? Whatever. I mean, I know that to some of you, this is old news. To some of you, you're just getting it now. And hopefully if you are just getting it now, you're getting it now. And to some of you, what I'm saying still might not make any sense, but I'm going to keep saying it because I think eventually it will. But sidebar, well, anyway, but hopefully it's clear if nothing else. I'm saying ultimately I'm saying a big analogy. Acceleration is to velocity as velocity is to position. I'm saying velocity is the rate of change of position with respect to time. Acceleration is the rate of change of velocity with respect to time. Therefore, if I have a velocity graph, the slope of any 2 points, the slope of the line connecting any 2 points on a velocity graph is average acceleration. And therefore, if this velocity time graph has a constant slope, just because I was told that it does, just because the problem just says draw a line with constant slope, then I'm saying, oh, here we have a situation of some object that has a constant acceleration. So this object is like an object in free fall. This object happens to have a constant acceleration of -4. In free fall, if we're measuring in meters per second squared, the number is usually -10, but the concept is exactly the same. And the number only reflect, like if we're willing to measure in different units, if we were measuring like in cubits, then free fall would be -4 meters per second squared. So don't let the number throw you. Everything I'm about to say about this would apply to an object in free fall. So in fact, let me go one. Do I want to go to the next one? Yeah, I have to say, I'll go to the next slide and I will actually start answering the questions in a moment. Forgive me. Let me say one more abstract thing about this. If you look at this graph now, I mean, the graph is monotonic. The graph is just going straight down, right? The graph is not changing direction or turning around or anything like that. It's just going straight down. But that's what the velocities are doing, right? The velocity begins at a value of positive 12 meters per second. Let's assume, in fact, I should have assumed, and please write this down. Or let me try to, I think I put it on the next page, but let's assume that by positive, let's make the choice of a coordinate system. Thank you, Galileo. Let's choose to picture a coordinate system in which positive means up, like away from the surface of Earth, and negative means down toward the surface of Earth. I'm just choosing that. I think you'll see that I write that on the next page as well, but that's okay. I'm choosing that. Again, that's a choice. You can call, sometimes like in the very last problem we did Monday, we called down positive. Sometimes that's convenient. Here, I think it's going to be convenient to call down negative. You can make whatever choice you want, but you have to make your choice clear. So I'm making my choice clear. And I'm saying with that choice, let's picture what this graph is telling me for a moment. This graph is never telling me at any given moment where the object is. It's telling me how fast and in what direction the object is heading. So initially, this object is thrown, let's say, it's given an initial thrust, an initial velocity of 12 meters per second in the positive direction. I'm now calling that the up direction. So this object is thrown up at 12. According to the graph, the velocity starts going down immediately. It immediately begins losing 4 units of velocity every second, right? So 1 second later, it's going to be, it's still going up, but it's going up slower now. 1 second later, it's been going 8 meters per second. Then the next second later, it's still going up. It still has positive numbers of velocity. It's still in the first quadrant of this graph, but now it's going 4 meters per second. And then finally, it hits the x-axis. In the graph, it hits the x-axis. The graph tells us velocity. So that means 3 seconds later, if I'm following this, 3 seconds later, the velocity of this object is 0. It doesn't mean it's at position 0. It means its velocity is 0. That means it has stopped. It has run out of velocity. For how long? For an instant. For an instant. Remember, its velocity is always changing. It's constantly accelerating. So for 1 instant, it's going 0 meters per second. It has stopped. But then what happens? Does it stop forever? No, because it still has acceleration. It still has an acceleration of -4. It's a constant acceleration of -4. So the very next second, it's now at velocity -4. So now it's coming down, right? Like, yeah, now it's coming down at a velocity of -4. Then another second later, it's at velocity -8. And finally, at the 6th second, just looking at the constant slope of this graph, at the 6th second, it's heading down at a velocity of -12, i.e. it's going just as fast, there's just as much speed as it had when it began this whole process, but now it's heading on its way down. So what this is, I just want to be as clear as possible. The graph just looks like, whoosh, the graph looks like something's just descending constantly forever, but the something that is descending forever is the velocity numbers. What the object is doing position-wise, space-wise, is it's going like this. Right? It's going up slower and slower and slower and slower until 0. And then it's coming down faster and faster and faster. Its speed numbers are getting lower and lower till 0. And then its speed numbers are getting greater and greater to something, to 12. But its velocity numbers are going +12, +8, +4, 0, -4, -8, -12. Like its velocity numbers are always going down. Its speed, you see what I'm saying? So this is a natural round trip. It goes up and then it comes down because its acceleration is always pointing down, right? In fact, the reason so its acceleration is initially pointing in the opposite direction from its initial velocity. How do I know? Because I'm told that the slope is -4, but the initial y-intercept, but the y-intercept is +12. They're in conflict. So the acceleration is trying to get it to go the other way. First, trying to get the velocities to go the other way. So it brings them all the way to 0 and then shoves them the other way. They slow down, then they speed up. This is a round trip under the influence of gravity. This is that, okay? Only this number happens to be 4, just so we can practice different math rather than the number 10. But this is how a round trip under free fall works. So that's a situation. It's a lot of discussion about the situation. That's the situation. So then we get to the questions. The first question is question A. Hello. The first, okay. So sorry. So this page right here just said what I just said. It's funny. I guess I'm thinking what I'm thinking. Yeah, so it just says this straight line graph is the VT graph for an object making a round trip free fall, a free fall round trip, a round trip under the influence of gravity. We started it with an initial velocity and it ended with it. The only distinction, right, is that in this graph, the example is -4. I don't know if you can see the thing because of the thing, but well, it says the only distinction in this graph, the A is -4, but in free fall, the A would be -10 meters per second squared. That's what it says behind the transcript, if you can't see. And please remember, of course, I'm going to, this whole screen, I'm going to PDF. I mean, it is a PDF. I'm going to put it into your Google Classroom when we're done. Okay, so that's just what that says. And then, okay, so now we're actually doing the problem. Problem A. So I say C diagram above because I am trying to do the 5-step method. C diagram above. Then it says assume t equals 3 seconds. What's x? Like I already asked, like where is the object? How far is the object? How far is Edna gotten at 3 seconds? Okay, by 3 seconds of its motion. Now, this is a really good question. This is a standard class. Like this is where we're in a zone of physics where, like again, I know different people in the room are at different levels of comfort in their mind. But here's where we get to something in physics where it totally, so they're asking, given this rate of acceleration, how far does the object get in a certain amount of time? This is totally doable. And once you get it, I don't think you'll think it's that bad. Once you get it, you get it. But until you get it, it's very conceivable that you don't get it. I mean, for all of us, like what I'm saying is, this is doable, but it's not self-evident. It's not obvious, or I don't think. Like we're going to use this graph and we're going to talk a lot about this graph. I am trying to say, by the way, this graph is classic. Anything that moves at constant acceleration, its velocity graph will be a straight line for sure. Its velocity graph will have a constant slope if acceleration is a constant. The graph is very illuminating and it will show us a lot of things, but I'm going to use it. But to get this answer, how far has the thing gotten in 3 seconds? I can't read that directly off the graph. Common mistake number 1 is, don't think that I can just go over to the value 3 on the x-axis, see what the value of, and see what the corresponding y coordinate or the corresponding v value is, and say that's the answer. If I look at where this graph is at t equals 3, I see that it crosses the x-axis. I see that the y coordinate when the X coordinate is 3 is 0. And that is definitely important information. It's definitely revealing information, but it's not the answer to this question. This question is asking, where is the object at the 3rd second? It's not asking where's the graph. And you might say, well, what's the difference? Or you might say, well, if the graph isn't telling us where the object is, what's the point of the graph? Remember, the graph is telling us how fast the object's going. If I read directly off the graph, what's going on at 3, what I find is that this object has an instantaneous velocity of 0 at 3. What the graph is really telling me, in other words, is that the object is at its peak height at 3. It's no longer having positive velocities, and it's not yet having negative velocities. It's at the highest place it's ever going to get. That place is what I'm being asked here. What I'm really being asked by this question is, how high does this object get if it's accelerating always downward at a rate of -4? That's what I'm really being asked. The graph will show me if I'm careful, but it doesn't just directly pop out of the graph. I'm being asked how high, how far away does this object ever get before it starts turning around? How far? Okay. So there's various ways to do this, some longer, some shorter. I'm going to walk you, I'm just looking at the time. Yeah. I'm going to walk you on the slightly long way first, because I think it's the most logical way. And then I'll show you the shortcut. Also, and by the way, maybe some of you may be bored or may be realizing, like, yes, the problem that I'm asking right now here, this is really the 3rd practice exercise that we're doing on the same type of question for what it's worth. Like, I think it's worth all this practice. But if you're thinking you've seen this problem before, you're correct. This problem is an example of a problem where we give you the rate of acceleration. We want to know how far something's gotten. And what we're really trying to drum into our heads is that, yeah, distance equals rate times time. Like, yeah, our whole life we've heard that distance equals rate times time. And yeah, if we know what that really means, there's truth to it. And yeah, physics is kind of all about, in a way, it's all about distance equals rate times time. But really what physics is saying is, whoa, there's a lot of different rates. There's a lot of different possible rates. There's average rate of velocity. There's instantaneous rate of velocity. There's average rate of acceleration. There's instantaneous rate of acceleration. Like, distance doesn't just equal any and every rate times time. When people say distance equals rate times time, what they really mean is distance equals rate of average speed times time. Distance most certainly does not equal rate of acceleration times time. It doesn't. And what we're really trying to say here is, when you know the acceleration of something, which you often do in physics, when what nature has made clear to you is the constant rate at which something is speeding up, then you can get the distance from that. And that's what we want to get. You could find out how far things are going, but you have to do a little work, because distance is 2 levels removed from acceleration, right? Acceleration is the rate of change of velocity. Velocity is the rate of change of position. So to go from acceleration to position takes something. It's not a direct leap. Okay, so we've done 2 other problems like this thus far with different numbers, where we were given the acceleration rate and we're trying to find out the distance. The first problem we did like that was that bicycle problem a week ago. Like, a bicycle starts from rest and it travels for 1 second, and how far does it get in that 1 second? That was the first example of this. And then the next example we did yesterday, when we did like this ball going down an inclined plane, and we did a bunch of things, and then we asked, how far does it get in the first second of this ramp? And we found out it got like a quarter of the distance, not a half. This is that same question again. If you feel like you're understanding that, then yes, this is that same thing again. I'm just showing you from a different angle. But say this were on an exam right now. Say this were on an exam. It's one thing for me to show you right ways to do this. I mean, like, that's what we always do in school. Let me show you the right way to do this. But what I firmly believe in my heart, it's not my job to show you the right way to do things. I mean, it is ultimately. But my main purpose of my job, the main purpose of you spending time on this Zoom with me, is not just to hear the right way of doing something. What you need to hear, I think, for the purpose of an exam, or for the purpose of like a life in scientific research, is you need to know, what do you do when you don't know what to do, right? If I just tell you what to do, then okay, if you know how to do it, then you do it. But like, if you already knew how to do it, then you wouldn't need me to tell you. What we all need to know is, what do we do when we don't know what to do? which is what exam problems always feel like. So I'm saying, let's look at this problem. We need to know how far the thing gets in 3 seconds, given a certain rate of acceleration. If I'm even on top of things enough to know that I cannot just read it directly off the graph. Also, by the way, I cannot just multiply 3 times -4 and say the answer is -12. Like a lot of people might do that. They might say, well, I've got this rate, it's -4, and I got the time, it's 3. So I'll multiply them. Distance equals rate times time. I'll say 3, I'll say the rate is -4, the time is 3, I'll multiply them and get -12. If you get -12, that is meaningful and helpful, and you're going to use that number somewhere if you're following what you're doing, but it ain't the answer. The answer to this question is not -12. And by the way, the straightforward reason for that is if you multiply 3 times -4 and get -12, then if you're watching your units or you're actually using the equations or you're carefully writing down GDPs and stuff, you'll realize that when you multiply 3 seconds times -4 meters per second squared, look at the units and you'll find that what you get is -12 meters per second. That's not how far the thing got. That's what rate of I'm sorry, when you multiply, yeah, what that is how much it's changed its velocity in that amount of time. What -12 represents is how much velocity this thing has lost during 3 seconds. That's not how far it gets. That's how much velocity it's lost. And by the way, it started with 12 and it loses 12. And that's why it ends up with 0. Like at this moment, it all kind of makes sense, but how far did it get? That's the question. So what do? I don't know what to do. I know just enough to know that this isn't as easy as I want it to be. So I don't know what to do if I'm in the middle of an exam or whatever. So I write down a GDP. I write down step 3. I write down something that is generally true. That's a definition or a principle that's reliable and vaguely topical. And I write it down before I even necessarily know what I'm going to do with it. I start writing things down that are true even before I see the finish line. And by the way, last sidebar, that's one of the biggest roadblocks to good science students, to successful science students, which you are, otherwise you wouldn't be in this class. Like one thing that gets people in trouble in physics at a certain point is they start getting used to that they did well in chemistry or they did well in high school, which I mean, you did, and I'm psyched, right? But what ends up a thing that gets in the way of smart, successful people is they start getting used to being smart and successful. And so they start thinking that that to do homework or to do something is to sit down and know what to do and then just do it. The reality of physics and the reality of science research is that when you sit down to do something, you don't know what you're doing until it starts happening. So we want to get used to starting things before we even know how they're going to end. This is the point of the 5-step process. That step 3 says, start writing things down that are true, even before you necessarily know what you're going to do with them. And don't let the fact that you don't know what you're going to do with them stop you from writing that. So I wrote average velocity equals display. So I'm really going to do this by cracky, I promise. God, I know everybody, like, the problem with this whole class is, like, I keep forgetting it's physics class. I keep thinking it's group therapy, and then everybody freaking needs to go find a therapist when class is over and their homework is still not done. Okay. So average velocity equals displacement per time. So I wrote that down because it's like always true. It's always true. It's a definition. Average velocity equals x minus x naught over t. Then I stop and say, okay, by the way, this x naught means the position at which the thing started, the initial position. Well, that means relative to 0. That means, like, where was it relative to the center of my coordinate system? Galileo says I get to pick the coordinate system. In fact, Galileo says I must pick the coordinate system. So I get to choose where 0 is. So I want to choose something that's convenient. So what I will often do, well, I'll always do when I can, is I'm going to place 0. I'm going to place the coordinate system, like in my mind, right on this object called Edna. I'm going to say that wherever Edna was at the beginning of this problem is what I'm calling position 0. I'm going to do that whenever I can, which is often. So often I'm crossing out x naught and calling it 0 and saying wherever Edna started, that is position 0. Just like whatever time she started, I mean, is when I started my stopwatch, that's called time 0. You might say, wait, if you can, like, so I do that a lot. You might say, if you're always going to do that, why do we even bother with the x naught term? Like, is there ever a time that we can't? cross out X naught? Well, two things. One, you're going to notice as we go through the problem, I'm not crossing out V naught. V naught is given as 12. V naught is not always 0. So first of all, I just want to emphasize that, like, not everything with a 0 is 0. V naught is not going to be crossed out. It's 12. Number one. Number two, yes, I cross out X naught and make it 0 whenever I can. But there is a situation where I can't. And that there is a situation where I can't. And that's if a problem happens to have two objects, which this one doesn't, but eventually physically will. If there's two objects and they start at two different places, then you can make where one of them started, you can call that 0, but then necessarily the other one can't be 0. So there is an importance to this X naught term often, and we have to think about it. But whenever we can, like now, when we only have one object, we make it 0. So I crossed out the X naught, made it 0. So that's also why sometimes I'm careless about, sometimes I'll write X minus X naught. Sometimes I'll just write X, because often I'm thinking X naught is 0. But okay, so I wrote V bar equals displacement over time. But what am I solving for? I'm solving for displacement. So I rearranged it and said, okay, X equals average velocity, displacement equals average velocity times time. Then I say, okay, I don't know the average velocity. No one ever told me the average velocity in this problem. Like, they didn't, it's not a given. And the velocity is a number that's always changing. So I don't know it, but I know acceleration is a constant. I know, therefore I can use all those constant acceleration equations. So I can say that in this case, the average velocity is the average of the velocities, the initial velocity plus the final velocity divided by 2, the average of. So I'm plugging that in for average velocity. Now, if this looks familiar, good, because yes, I've done this before. I'm just doing it again. So displacement equals average velocity times time, right? And then I go, okay, I'm making some progress here. I'm looking for displacement. I know displacement is average velocity times time. But now, do I know the final velocity? Like, I know the initial velocity was given as 12. Do I know the final velocity? Well, let me turn the page and find out. Well, and what do I mean by final velocity? I mean the velocity finally at the end of what I'm investigating right now, not at the end of time, not at the end of the universe, and not even at the end of this whole problem, just at the end of the interval that I'm looking at right now. In other words, if I'm going to be plugging in 3 for t, then by v, I mean the velocity at the end of those 3 seconds. Whoops, someone's here. Right? That's how. So by v, I mean the instantaneous velocity at the 3rd second. Do I know what that is? Well, that, number one, that is something I can read off the graph. The graph is telling me velocities at certain times. According to the graph, the velocity at t equals 3 is 0. Like we said that before. Yeah, right. The velocity is 0. We said that a minute ago. Like if you just look at the graph, what's v when t equals 3? It's 0. Like when t equals 3, the graph crosses the x-axis. Does that make sense? I think it makes sense. Like I was saying before, if you picture that you're throwing something up at 12 and it's I'm saying throwing up, like on Earth, it would be losing 10 every meter. It would be losing 10 meters per second every second. Let's imagine that we're instead throwing it up on Mars or something where gravity works the same way, but just is a slightly smaller number, right? This is all, and this whole problem is like an analogy to gravity. It's the same concept, just a different number. So if I threw something up at 12 and it lost 4 every second, then 12 divided by 4 is 3, or 12 divided by 3 is whatever. If it lost 4 every second, then 3 seconds later, it would fully run out and be at 0. That's what the graph is saying. That's what I'm conceptually saying, that it takes 3. If I throw something up at 12 and it's losing 4 every moment, then at t equals 3, it's going to be at v equals 0. If you don't believe me, or you're like, oh, that's too, can we just like do real physics here? Well, look at this is the definition of acceleration. Write down another equation that you know is true. That's definitely true. Definition, always true, of average acceleration equals v. So I'm in the middle of the page now. I'm looking at the black writing. A bar equals v minus v naught over t. Now we know that we know that the acceleration is always the same. So even though that's the definition of average acceleration and instantaneous acceleration are all interchangeable with initial acceleration in this context. So I don't even have to worry about the bar anymore. So I say, and I'm trying to solve for V. Like I think the answer is 0. I'm just trying to show you more than one way to establish what the final V is. And by the way, again, why do we need it? Because we need it in order to average it. We need it because of that equation written at the top of the page in black. If we're going to get the average velocity, we need two velocities to average. So this is the one that's missing. So I'm solving for V. I just rearrange AT equals V minus V naught. I'm back at the black writing at the bottom page. I arrange AT equals V minus V naught, add V naught to both sides. So V equals AT plus V naught. Now again, notice here, this is V naught, not X naught, V naught. So it doesn't cross out. It's not 0. It was given as positive 12. Now here also, like the transcript might be getting in your way of reading this. And I can't move. Can I move this? Oh, wait, maybe I don't know what to do with. But what it says at the bottom is V equals -4 times 3 plus 12, right? I'm just plugging in now. So V equals -12 plus 12. Which equals, even though you can't read it behind the transcript on, I don't know if your screen looks like my screen, but it has V instantaneous, V with no bar on it. The instantaneous V at the moment of t equals 3 is -12 plus positive 12 equals 0. Like, so that's just like a little proof of what I've been trying to say. I'm saying the thing started with 12 units of speed and it loses 4 every second. It does so for 3 seconds. So it loses all 12. And it starts with 12, but it loses 12. That's what the 12 plus -12 means. It started with 12, but it lost 12. So it ends up with 0. Okay. Now, have I answered the question? Luckily, by the way, this question that I'm answering is the longest of all the other questions. Go a little faster than this one, but have I answered the question? No. This 12 that I just got, that's what I was saying before. That's just the velocity information. The question is asking me for how far the thing has gotten. Now I've learned that in those 3 seconds, it's gotten down to a velocity of 0. So now I have something to plug back into my average velocity expression. So I'm going back to displacement now. So I say, okay, X equals V naught plus V over 2 all multiplied by T. Now I've got everything to plug in there. V naught was 12, V is 0. I'm averaging, and T is 3 seconds. So I average 12 and 0 together. I average them, I get 6. So the ultimate answer here, the ultimate answer to this question, to this homework question, 6A, is 18 meters. To back up for a second, what I'm saying is, this object that started with a velocity of 12 and lost 4 units of velocity every second traveled 18 meters in the first 3 seconds. It traveled 18 meters. Now, I'm also saying this is just like the problem we did 2 days ago, the problem of a ball on an inclined plane, like a baseball rolling down a slide. And it's just like the problem of the bicycle a week ago going forward. They're all the same in that you're given a rate of acceleration, of constant acceleration, and you're trying to figure out how far something's going. But you know, the arrangement of the problem is slightly different each time. Like in this case, in the other 2 cases that you did, the object started from rest and was speeding up. This object started from some high speed and is slowing down. Still the same concepts. But I really do want you to notice that this number 18, like I'm saying, how far will this number, how far will this object travel in 3 seconds? 18 meters is the answer. I think the answer makes a lot of sense. I'm going to show you with more discussion how I'm going to show you more ways to see how I think it makes sense. But let's make no mistake about it. It might make sense and it might even be right. I mean, it is right, but it's not obvious. It's like not a number that would have popped into my mind when I just looked at the numbers in the problem. Like it's not something like it's 18. The numbers given in the problem were like -4 and 12 and 3. How, like if I don't know what I'm doing and I just like try to gut through, or I just try to memorize formulas and just plug them in or whatever, or, I'm not going to get it right. And I'm not saying that to be intimidating, but it's not like I could look at it's not what I initially would think. I would think maybe 4 times 3 would equal -12, or I read off the graph that at 3, the answer is 0, but no, none of those things. The answer is 18. It's like, it's out of nowhere. Oh my God, things are happening. Sorry, there's a lot of interruptions. So one question is, where did is 18 something that I could even see in the graph? Like, what did the graph do for me? If the answer is 18, like, where the heck is 18 in this graph? Where do I see 18 in the graph? Well, the answer is yes, 18 is in the graph if you know how to read the graph, but you have to know how to read the graph. So I'll show you. Okay, let me go to the graph first. So let me show you. Yes, you can see it in the graph. Let me turn back to the graph and show you. Oh, and hold on, bear with me for 1 second. Let me just hold on 1 second. Okay, sorry. So look at the graph. Yeah, so here's a graph. You notice that I shaded the area between the graph and the x-axis, like that triangle there in the first 3 seconds. I shaded that area. Now look, the height of that triangle is 12. The base of that triangle is 3. The area of a triangle is 1/2 base times height. 1/2 times 12 times 3 is 1/2 times 36, 18. That is not a coincidence. I'm saying 18 is the area of that triangle between the graph and the x-axis. It's the so-called area under the curve. They call it the area under the curve. Now, this line happens to be straight, not curved, but by curve, they mean whatever the graph looks like. This 18, the distance, is the area under the curve. That is not a coincidence. First of all, it's not a coincidence because what some of you might know in some part of your brain somewhere from some calculus class is that the area under the curve is a way to understand the calculus concept called integral. Right? Now, don't be scared. Just stay with me for a second. You may remember that whatever the integral is, the continuous sum along a curve, the integral is often computed or understood through the fundamental theorem of calculus to be equal to the antiderivative. The integral, right? The integral of a derivative of a function is the original function itself. To integrate is to take a derivative backwards, you may recall, right? Integrals are the inverse function of derivatives. It's not obvious at all, but it turns out to be true. It's very bizarrely true that when we want to take integrals, we do derivatives backwards. Well, remember, velocity is the derivative of position with respect to time. Velocity is the derivative of position with respect to time. Therefore, position is the antiderivative of velocity. If we want to look at a velocity graph and find out where we are, we're doing derivatives backwards. We're taking integrals. So it's actually not a surprise. It actually makes sense that to figure out how far you've gotten from a velocity graph, you could look at the area under the curve. Kind of cool, actually. But then you might say, great, that's fabulous, Yaverbaum. I'm glad you like calculus and you think that bringing up some calculus point is going to make the physics somehow more interesting or more clear. It doesn't make it more clear to me, you might say, because I never liked calculus, you might say. Well, I'm here to say, fine, I totally understand that. And that was me too at one point. But maybe a different way of putting this is me saying, maybe this helps with calculus a little bit. Like there's a reason that the integral is the area under the curve. There's a reason that this works out. Let me put it this way. The area under this triangle, the area of this triangle is 1/2 BH. 1/2 BH. It's kind of like saying 1/2 velocity times time. Why would position, why would displacement, like you might even think I would kind of understand if he was saying like distance equals rate times time, but why the heck 1/2? Where's the 1/2 coming from? Because displacement equals average velocity times time. Average velocity times time. And if you notice our calculation, the average velocity, in order to get it, we had to average two velocities, one of which was 12 and the other which was 0. So the average velocity was 1/2, which was 12 plus 0 divided by 2. It was 12 divided by 2. It was this. In other words, we had to take half because we're not always going the same velocity. If we took the area under a horizontal line, the area there would just be a rectangle, velocity times time. But this velocity is always decreasing. So to take the velocity times the time, to get that, we actually have to take the area of a triangle, not of a square, because we don't want to multiply every one of those time units by the same velocity. The velocity is going down. We multiply by the average velocity, which in this case is the maximum plus the minimum, well, which is always the maximum plus the minimum divided by 2. The minimum was 0, so it's half of the maximum. So the displacement was in effect 1/2 the initial velocity times the time. Or in other words, it was 1/2 the acceleration times the time, right? The acceleration times the time got us the velocity. It was 1/2 the acceleration times the time, velocity, times time. In other words, to say this quickly, everything we just did in a number of steps, we could have just all put together in one algebraic thing. If we just summarized what we all did algebraically, you've seen this 1 week ago, I'm doing it again right now. If you just say, okay, displacement equals, so I'm here. If you say displacement equals average, well, the arrow will appear in a second. There's the arrow, yeah. Displacement equals average velocity times time. And then you're like, oh, average velocity means initial plus final divided by 2. Oh, I don't know what the final is. I have to figure it out by saying it's acceleration times time plus initial. And you do that out. Then you end up finding out that what you're really saying is initial velocity times time plus acceleration times time. Sorry, you're saying 1/2 of acceleration times time. That's 1/2 of the gain in velocity. What the average velocity times time. So in order to get this whole answer, we could have just plugged into this equation that we developed last week. We certainly could have. It would be a lot faster. I'm just trying to show you why this equation makes sense and where it came from. This 1/2 AT squared. Why it's 1/2 AT squared is we're really saying area under the curve, if you like, or we're really saying is average velocity times time. In other words, if you just plug into that equation, you get 1/2 times -4 times 3 squared plus 12, 3. Like I'm just showing you that we could have just plugged into that equation, and that's perfectly legitimate on an exam or whatever else, as long as you know what you're doing and you show all steps. It is faster. That equation is just a summary of, but you have to know what you're doing to do that. If you don't know what you're doing, you do what you do when you don't know what to do, which is go through fundamentals, and they'll lead you here. So that trick would get 18, which is to say 36 plus -18. So that's the answer, 18. So you could have plugged in. Now I've got one more minute. Well, here, I think, so then the next question, I'm just going to bang through the rest of the answers, but they're in this packet that you can then look at, and they'll be the answers to the homework. As long as you understand them, good. So question B was, how far has it gotten? Where is it? Was that the question? oh yeah, how far has it gotten in 6 seconds? Well, by that point, it's gone all the way back. But if it took 3 seconds to go up and lose all of its velocity to get to a peak height, it takes another 3 seconds to get all the way back to where it started, displacement 0. So that's, and you could check that with the graph, you could check with equations, but if you're understanding the whole concept now, you can see that in 6 seconds, it's back to where it started. Then it asks in C, at question C, it asks at t equals 3, what's the acceleration rate? Let me be very clear. Right off the graph, you can read that the velocity at t equals 3 is 0. It's not moving at all at 3, but it still has acceleration. It has the same acceleration it ever did, which is -4. If it did, in other words, just because you're not moving doesn't mean you're not accelerating. You can have 0 velocity, but still have some acceleration. And in fact, you better whenever you get to the top of a natural gravitational round trip. Because if you got to the top and you had 0 velocity and that meant that you also had 0 acceleration, then you would never change your velocity and never come back down. You would hover. So the answer to C, so the answer to C is -4 meters per second squared is the acceleration. Then it asks when she's speeding. I know we're done. I'm just about to, if you have to go, go, but I'm just done. I mean, I'm done in 1 second and I'll just hang out. But yes, enjoy the rest of your day. I mean, they're done. And all the rest of these answers are in the packet. I mean, in the PDF, which will be uploaded. So, I mean, we're good. But yeah, I'll just say for anybody who's still here, and the speeds up when her velocities are getting increasingly negative. In other words, in the last 3 seconds, thank you, guys. Thank you. Awesome. In the last 3 seconds, she's speeding up. In the first 3, she was slowing down. And then finally, there's a chart. It asks you for a chart. Here's the chart. You should look at the chart at home and make sure you understand where I got everything. But yes, thank you. I'm done. Sorry, that's it. This will all be uploaded. That's good. Have a good day. Have a good day. All right, I'm done. Enjoy your week. Yes. Awesome. Have a nice day, everybody. Yes. And you're good, Kevin, or are you still there? Oh, cool. Okay. Hi.